All right. So, welcome, folks, to the today's Bridges-2 webinar. Would like to welcome you on behalf of the Pittsburgh Supercomputing Center, uh, celebrating its 40th year of service to the national research and education community, and in particular to the Bridges-2 project, which is a National Science Foundation funded project to provide advanced computing and data resources to the community. My name is Sergio Sanilevich. I'm the principal investigator of the project, of the Bridges-2 project, and this is our leadership team here. And all of us thank you for attending today. So this event is part of our Bridges-2 webinar series, which we started back in 2023 as a forum for the Bridges-2 community to learn and share ideas and achievements. And um, if you do a search on Bridges-2 webinar series, you will find like the recordings of all the past webinars. And if you check in a couple days, this one too will appear with its recording and the slides that Niraj will present. So the idea is to have topics and speakers of interest to work that is being done or that may be done in future, preferably but not exclusively using Bridges-2 resources. So if there's something interesting that you do on another resource, but if you think the Bridges-2 users might be interested in it or the community at large, then just contact me and we'll discuss it. And I'd be we would obviously be very grateful. It could be your work, of course, as well. So today we are happy to hear from Dr. Niraj Nepal. And you see his short bio here. He works here at the Pittsburgh Supercomputing Center since January 2025. And he works on a variety of things of interest to the community, including ab initio methods, quantum computing, and AI. Before we turn things over to Niraj, just a reminder, we do abide by the code of conduct of the Access project, which of course is Bridges-2 is a provider on the Access as well as on the NAIR. During the talk, all of us except Niraj will be muted, and we would invite you to type your questions into the Zoom chat. We may be able to answer some of them, but then after the presentation, we will have 10 minutes, the last 10 minutes for a Q&A session. And there will be, again, a video recording of this webinar and the slides on the Bridges-2 webinar series slides. So before I turn things over to Niraj, does anybody have any questions for me? If not, thank you very much. And Niraj, please take it away.
Thank you, Sergio. And hello, everyone. Good afternoon, and welcome to today's webinar. Let me share my screen, and then I will turn off my video. So, do everyone can see my slide?
Not anymore.
Yeah, I think you turned off your slides now, Niraj.
Yeah, sorry about that. So now?
It's good.
Yes.
So yeah, welcome everyone. So these are the outlines of the talk. This talk is more like introductory QAOA algorithm, like classroom style talk. So I will discuss theoretical framework, including many different uh, terms within this pipeline, and the talk will mostly focus on max cut problem, which is a simple theoretical problem used for benchmarking purposes. But this algorithm will be like scalable to other real life examples where I will show you mathematical formulation and also the Python code. And finally, we will show some commands to how to run a CUDA-Q on Bridges-2. Uh, for that, I will provide a GitHub repo and a recorded demo for you to explore later after the talk. Uh, but I will explain the commands on this talk. Okay. So QAOA, the full form is like Quantum Approximate Optimization Algorithm. It is a hybrid quantum classical algorithm to solve combinatorial optimization problem. So it has two components, parameterized quantum circuits, and it uses classical optimization for self-consistency. And it is useful for near-term NISQ quantum hardware. And I think this is one of the couple of applications uh, will be scalable to real life scenario in industry or academia. So it is this algorithm is applied to many problems like max code, scheduling, routing, and portfolio optimization. Uh, so there are various flavors of QAOA. You can check out this review paper, and you can see it has various you can tune it from this original like standard QAOA, which we will be discussing in this talk, and then you can get a whole lot of these different flavors having different like can be applied to different applications. So this is overall theoretical framework. We will go to each of these part and discuss in terms of max cut problem. First, we have to define our optimization problem, which is like combinatorial optimization problem. It can have multiple solutions, but we want to find optimal solution among those solutions. And these are some of the problems this algorithm have been used in recent years. For example, here we have North Wales Police and D-Wave using this algorithm for optimizing police vehicle placement, and Dative using IQM hardware, uh, exploring this algorithm for portfolio optimization. Similarly, it can be used for logistic optimization, supply chain optimization, and also can be used in science problem. Here we have physics higher order Ising spin glass model solving with QAOA. Similarly, it can be used for like biophysics problem, finding low energy conformations of lattice protein models. So next, we have to define our cost function or objective function that can be like either maximize or minimize depending on the problem, and it can have a constant as well. And to go through using quantum hardware, we have to make sure we satisfy this formalism called Kubo formalism. And so because many combinatorial optimization problem can be converted to Kubo and solved with quantum computing. As in the name suggests, it has a quadratic objective function, and there should not be any constraint on those cost function, and the target vectors should be binary containing 0 and 1. And if we have constraint, for example, if we do portfolio optimization, we should have like we'll have some budget constraint, like we need to buy stock and bonds for certain budgets within the certain budget. So that will we have to like that constraint will act on the problem. Then we can transform them into penalty term and add it to the cost function to make a new cost function, and we can work with. So here we can see the first two terms are uh, classical like quadratic objective function, like normal objective function, and the third term is the constraint for violating this constraint here. So lambda is the penalty constant or something like that. Okay, so let's discuss what this problem is. It is called max cut problem, and this is a theoretical kind of problem. And we have the graph with different nodes. Like we have here 5 nodes, and we have edges between these two nodes. And our problem is like our goal is to partition this set of nodes into two complementary subsets labeled by 0 and 1, and we can do that with maximizing the number of edges that shares two different type of nodes. For example, here we can see there are six edges here, but we have like 5 edges that has two different nodes. And with that, if we simply cut a dash line through those edges, we can see that these two nodes are within the this cut, and other three nodes are outside of this cut. So that's the partitions we are talking about. And to do that, we have this cost function here, and wij is the weight of the edges. Since here we are assuming as an equal weight, and also non-directional, like on-directional. It doesn't have any direction in those edges, so this will be symmetric. And in this term, we can see that these terms contribute to cost function only if xi is 1 and xj is 0. That means if these two nodes of the edges falls in different category. Otherwise, if they are all both of 0 or both 1, they contributes nothing to the cost function. That means when we include more kind of edges with different nodes, our cost function gets maximized. And we can rewrite this in a simple terms like this. And then in matrix form, it looks something like this, like as a quadratic cost function. So our goal is to maximize this cost function. But in quantum computing, we generally find a ground state solution of the Hamiltonian we have. Therefore, we can simply put a minus sign in front of this cost function and minimize this function. So this is how I have defined this graph in the tutorial. We will discuss each part of the tutorial along the way as well. And here we have a graph with 10 nodes and 14 edges given by this one. And we want to find like partition these nodes into two different subset such that our cost function gets like maximized, or negative of cost function gets minimized. So this is a very simple, like very small problems, but uh, there would be in real life there would be very complex graphs as seen over here. This is some kind of delivery route. You can see some warehouses somewhere like in the middle of Europe or something like that, and you have these users for which you have to deliver your stuff from these warehouses. And this kind of problem this QAOA can solve. And when we have like more Q nodes, then we in quantum computing we need more qubits, and or we have to handle them differently, different solution, and that makes classical computing very expensive and unmanageable. So next, since the cost function cannot directly employ to quantum hardware, we have to formulate this uh, in a way that quantum hardware can understand. That's uh, converting them into Hamiltonian, and then using the quantum gates, we can solve this problem. So first, we need to encode our cost Hamiltonian. So it is called Schrodinger equation, where we have this operator, Hamiltonian operator, which we do not know, but we know the cost function, and we also don't know the this quantum state encoding a bit string. That means this is simply a string of nodes, uh, either having a value 0 or 1. And similarly, we can compute using this expectation value. So this is called expectation value. Is simply the average value of this Hamiltonian in the distribution of this quantum state. Still, we need to find this Hamiltonian operator. To do that, we have to do something called like Ising transformation. Ising terms comes from like quantum mechanical system of spins of like electronic like spins having a different orientation. Uh, So yeah, that way, if we can encode our problem Hamiltonian into those kind of problem, then we can easily solve with quantum computers. So to do that, we have to define this Pauli spin operator, G. So there are three different spin operator like X, Y, G, and identity operator forms a like complete basis. So here, when we apply this operator to our state xi, so it can be either 0 or 1. And we can see that if the state is get 0, and we can define it this state by get xi or get 0 or get 1. And if it is 0, then we will have +1 eigenvalue. And if it is 1, then we will have -1 eigenvalue. Similarly, we can simply say, okay, gi, let gi be the eigenvalue of this operator. And we can rewrite this expression as 1 minus 2xi. And if you substitute 0 or 1, you will get 1 or -1 depending on your state. And that means we can compare 1 minus 2xi, like we can equate this to gi, and we can get xi as in terms of this gi. Now we can substitute this eigenvalue this terms in terms of gi into cost function, and then change this gi to like capital Gi operator. Then we will get this cost Hamiltonian operator, and we can see that this has this identity like unitary matrix identity matrix term, and then we have this 2-qubit GG gate that where this first operator act on ith qubit, and uh, another operator acting on j qubit of the same edge. So our goal is to find highest energy state of cost Hamiltonian, this one, or since in the quantum computing we explore like to get like minimum ground state energy, so we can simply put negative sign over here and redefine our cost function. And we can see that we have switched the sign over here. So in terms of CUDA-Q, so this is the Hamiltonian, cost Hamiltonian we want to encode, we want to define, and here we have weight equals to 1 if they belongs to edge. And we can say the operator we want to like load is spin operator from CUDA-Q. And we can see that like for each individual edges of like source and target, we are building this operator like with using spin.g function here, and spin.I is the identity operator. And if you printed the Hamiltonian, you can see that it's a spin operator. Next, so now we have to solve this Schrodinger equation, but it cannot be solved very easily because it's a combinatorial optimization problem, and there involves many nodes in the graph. So sometimes we may stuck in the like local minima or something like that. So we have to find a better way to solve this problem. For that, we will use adiabatic theorem. So yeah, as I said, solving this equation is computationally intractable because first we have to start with a robust state preparation, right? We have to begin with something that we can like eventually lead to the ground state. And searching solution through a Hilbert space of like this 2 to the power n dimension is quite challenging because as the number of nodes grow in the graph, then we will also require a very huge number of qubits. And sometimes if your different solution can have like a similar kind of energy, then sometimes systems can get trapped into local minima, and then you may not get out of it. And in the quantum hardware, solving this equation requires state preparation, but also very good fidelity like gate operation as well. And that's in terms of right now in the NISQ era is quite challenging. So it's easy to use a different approach. And in terms of computation, as you can see, it scales like the state scales 2 to the power n, and the operator scales even like 2 to the power times 2 to the power n matrices. So it becomes very, very huge even in the computation. So solution is one can start from a simple Hamiltonian called mixer Hamiltonian, which we will discuss detail in later. And we can slowly evolve the system into complex Hamiltonian over the time. And the system, with that system, adiabatically follows from the initial ground state of the simple Hamiltonian to that of complex Hamiltonian without jumping to excited state. So I can put this scenario in two different situations where we do not know the destination, but in the first picture, you can see like he doesn't know from where to start and which path to follow. But in the next, you can see there is a well-defined entrance and then there is a well-defined path here. So that even though he doesn't know where the destination, but there is a chance he might get there eventually. So this is the adiabatic theorem we are talking about. So mathematically, we can see we have to define a Hamiltonian such that we have both terms, mixture and cost Hamiltonian, and the AT and BT is the time-dependent term given by this expression. And you can see at when t equals 0, this term will not contribute, does not contribute, and the Hamiltonian is totally contributed by mixture Hamiltonian. But as we increase the time and we reach up to time t, capital T, and in that time this term becomes 0, and we only have this cost Hamiltonian term. Now we can rewrite this as a like time-dependent mixture and time-dependent cost Hamiltonian, and their time-independent part can be defined here. So mixture Hamiltonian is simply the negative of this xi gate, Pauli xi gate operating on all the qubit. Why we are choosing this Hamiltonian? Because its ground state is very easy to prepare. As you can say, you only have to apply H gate, Hadamard gate that creates a superposition state like of two like 0 ket and 1 ket state, and like equal superposition like they both of them has like almost equal probability. And the cost Hamiltonian we have here is much more complex than this Hamiltonian, and we need to slowly like evolve in the time from this Hamiltonian to this Hamiltonian. And if we do like faster, then our system can like move to excited state of this Hamiltonian. So we do not want that. And the time scale also depends on the energy gap between these two states, like ground state and the first excited state. And with that, when we slowly move from this Hamiltonian to this Hamiltonian over the time, then the ground state that we can actually calculate and know from like of this mixed Hamiltonian automatically evolves into ground state of this cost Hamiltonian. And now the problem is now our Hamiltonian becomes time dependent. So before we have a time independent cost Hamiltonian, but now we have time dependent Hamiltonian. So which requires this time dependent equation to solve. And this is the equation, Schrodinger time dependent equation. And I is the imaginary complex number, is the square root of negative of 1. And the solution can be obtained using this expression here. So get psi 0 is the state, our quantum state at time 0. And we will use this time evolution operator to get our state at any later time t. And this time evolution operator is defined here, which is simply exponential of negative imaginary number and the integration of this time-dependent Hamiltonian. And you can see this, we have a time ordering operator because we want to keep evolution in correct time order. If we simply switch our Hamiltonian in different times, then we will get a completely different state. So this will make sure that we will apply our Hamiltonian at different time in correct order. The reason is that because these Hamiltonian in individual time step does not contribute to, I mean, does not commute with each other. So first, in the numerical simulation, we have to discretize this integration in sums. For that, we have chosen this time step delta t, simply p number of times. And when we use that in the time evolution operator, we can see this product of these individual the sum over here will change into product in the exponential part, and inside that we can expand h in terms of hm, mixed Hamiltonian and the cost Hamiltonian, and we still have this time evolution operator here. So since now we have operator in terms of exponential, and then we have these two sums, right? But since this is a complex operator, we cannot apply this state sequentially to any, I mean, this operator sequentially to any state. So we need to break these two term, like for like exponential mixed Hamiltonian and the exponential cost Hamiltonian. So to do that, we use something called like Suzuki-Trotter expansion. This is the first order expansion. If we have two non-commuting operators, HM and HT, we can simply express them in terms of multiplication, but there will always be error in terms of like this delta t square. And you can see like if we make this time scale in small enough such that this terms becomes much negligible. So then in that case we can expand our this exponential operator of these two summation of the Hamiltonian into product of these individual Hamiltonian. And the non-commuting operators means when we apply these two operator to this state, the ordering matters. For example, if we apply xg to get zero state or gx to get zero state, first the g operator will act on this, and then in that case we will get the positive eigenvalue. And if we reverse this operation, as we can see, x will act on the operator state first, and in that case we will get the negative value. So, this with this we can say these x and g operators are non-commuting operators. Now we can use this totalization into our time evolution operator, and then we can get this equation. As you can see, there are p terms. I haven't listed the terms in between. So this is the first term, and this is the p and the last term. So with this, we can include this as a quantum circuit. So now we have all the ingredient to build a quantum circuit. Basically in this circuit, we will prepare our N-such state, and then we perform the measurement on those state. Basically, we will calculate the expectation value of the cost Hamiltonian, and we will compare with whether they are in the ground state or not, and then update parameters using classical optimizer. So this is what it looks like. As you can see, we start from this initial state with like qubit get zero state for all the qubits. Then we apply H gate, Hadamard gate to all the qubit to prepare equal superposition of like this 0 gate and 1 gate state. And this is the initial state, I mean ground state of the mixer Hamiltonian as well. So now we have encoded those exponential multiplication into this layer of like gated circuit here. And we apply first like cost layer and then a mixer layer. And as you can see that we have parameterized our delta t in terms of beta and gamma. Gamma is corresponds to cost layer and beta corresponds to mixer layer. And once we prepare the state, we finally measure the state in terms of like expectation value of the cost Hamiltonian to get the cost function or object like calculate the objective function. And in the CUDA-Q, the tutorial I have provided, you can see these lines over there, where qubit counts is simply the length of the nodes in the graph, and we can define our this number of layers. Even within this layer, there will be two like sub layer or something like that corresponds to cost and mixture, and the parameter count would be 2 times of this layer count. So this is the standard QAOA, but in like multi-angle QAOA, even individual like summation terms can have different parameters, but that's a different story. For this, we will stick to a single parameter for each layer. So this is the decomposing that layer into a very fundamental block. For example, if we go down to cost layer of one edge, right? So we have a cost layer of one edge involving I and j as a node. There, in that case, our Hamiltonian will be like exponential using this expression, and you can, if you substitute this formula over here for one single edge, because this is the same Hamiltonian operator but without summation over INJ. And if you substitute, then you can see that this is the operator we have, and the identity operator can be rewrite as a constant over here. And this expression is nothing but the uh, 2-qubit GG rotation gate. Similarly, for the mixer, we can apply this XI gate for each node in the mixer Hamiltonian. If we substitute this to over here, then we get this expression here, which is nothing but 1-qubit X rotation gate here. And and so the GG rotation gate over here is sometimes native on some quantum hardware. Native means they are implemented within the hardware, so they don't have to be create like closer operation to that. Like they don't have to like decomposed into other gates. But for example, that exists in IonQ Fortray quantum hardware, but it must be decomposed to other available native gates if it is not present there natively. So to do that, let's see, this table is kind of complicated, looks like complicated, but it's very, very easy. For here, like I have shown the formula to be focused on this box here, like a square rectangular box. As you can say, this is the 2-qubit GG rotation gate applying to the state of like IJ, and we have this eigenvalue e to the like minus I theta lambda over 2. If I and j are equal, so lambda is +1. If I and j are not the same in the same state, then we have -1, and it makes the sign over here plus. As you can see in the table here, when there is both 0, 0 and 1, 1 state, we have exponential like a negative sign in the exponential over here. But when we have switched the we have changed one of the qubit here, then now we have used this lambda equals -1, making like positive in the exponentials. And so this can be decomposed into this series of these gates. First applying C NOT gate. This is the control NOT gate. It will so this is basically applying X gate to the J qubit, depending on whether this first qubit, the control qubit, is in 0-gate state or 1-gate state. So as you can see, let's start with here. Since the first qubit is at the 0-gate state, it will not change, this gate will not change the another state. So we can say in both, if the both the this qubit in 0 state, we have not changed this another state here. But if you have a control qubit in one state, then we can see that the 0 is flipped to 1 and 1 is flipped to 0. And in the next part, you need to apply this rotation gate, qubit rotation gate to second qubit over this qubit here. And you can see that when it is over here, when we apply this gate to 0-gate state, then this -1 over 0 becomes like +1, and we will have a negative sign in the exponential. But if it is applied to one state, 1-gate state, then it becomes plus. As you can see here, if it is 0, we have this negative sign over here. But if you have 1 over here, sorry, if we have 0, we have negative. If we have 1 in the J qubit, it becomes plus here. And finally, we again apply the C NOT gate to switch the order of this gate back to the original state here. So basically, we have decomposed our 2-qubit rotation gate in series of these 3 quantum gates. So in the CUDA-Q, we can define them in this way. First, this is the cost Hamiltonian operator. As you can see, first we apply C NOT gate, followed by rotation, G rotation gate, and then followed by control NOT gate or control X gate as well. So you can say either C NOT gate or CX gate. And in terms of full QAOA circuit, first we are preparing our ground state of mixer Hamiltonian by simply initializing these state in 0-gate state, and then we apply H gate to all the um, like all the qubits in the state. And finally, we have used our cost layer in the for all the edges to build those gates for the quantum layers. And then also, again, we apply mixer layer, which is simply the rotation, like X rotation single qubit gate. And these we are applying this, constructing these uh, uh, like a problem in like different layers, like until we have like reached the layer count. So next, since we have prepared our state, and also we can perform our measurement. Now next step is to use a classical optimizer to check our result and then update parameters if needed. So basically, it is follow these steps. We evaluate energy for each N-SAS wave function for different parameters, and update parameters for next iteration. For example, we can initialize our gamma and beta, and then we construct this time evolution operator for cost and mixer layer, and then we can apply in this order to the our initial ground state of the mixer Hamiltonian. And finally, we compute the expectation value of the cost Hamiltonian with this NSAR state. And then we will evaluate the energy, and we will compare either to previous earlier iteration, energy from earlier iteration. If it is not converged within the convergence criteria, then we will compute the gradient of the energy with respect to this parameter and update the parameter with classical optimizer. So this process is repeated iteratively until convergence criteria or maximum iteration is achieved, and this process is uh, carried out in classical machine. And optimizer is basically, there are two type of optimizers, like direct search optimizer and gradient based search optimizers. So this is how you define those objective function in CUDA-Q. It's simply we are using CUDA-Q.observe function with the kernel followed by Hamiltonian, and then we list the parameters like arguments of this kernel. And once we build that object, then we can invoke this expectation method to get the computing, like get the expectation value of those Hamiltonian. And in classical optimization here, we can use CUDA-Q dot like optimizers module. And here I have used like this constraint optimization by linear approximation methods. And the initial parameters play a very key role in the convergence. For example, if we use -1 to 1 in the tutorial, you can get the converge result even in the two layers. But if you have use -pi/2 to pi/2, then convergence requires more than 3 layers. And in the code, you will get this result in something like this. And you can see that there is the expectation value, optimal expectation value after convergence printed out, and then these parameters. Once we get these parameters, we will again use that parameters to sample our kernel one last time, like one final time with like maybe 1,000 times in 1,000 sorts or something like that, to get the probability distribution and get the our final ground state result. So this is the, so far I have discussed the theoretical description of the QAOA. Now I will discuss how to use CUDA-Q on our machine. So first, let me start with what is CUDA-Q. It is simply NVIDIA's hybrid quantum classical platform. So it runs on both classical hardware, CPU, GPU, and then on the real quantum hardware. So you can access these QPUs if you have accounts and allocations in this any of the QPU vendor. You can use those using CUDA-Q. It is open source, easily integrates with HPC and AI workflows. It also supports error correction and noise modeling. And using this is very simple. Like, say you simply import CUDA-Q, and then you can use other methods or functions from this CUDA-Q module. And in detail, you can visit this link. So let me start. I have prepared like this GitHub repo. In this path, you can easily download them using a git clone method. And there are a bunch of files, as you can see. And there's a maxcode.py Python version, and there is also like Jupyter Notebook version of it here. And in Bridges-2, if you go to this path, you can find this container. If you want to use elsewhere, you can alternatively download CUDA-Q in this link here. So you can run this CUDA-Q in every scenario, for example, in interactive session or in batch mode or in Jupyter Notebook as well. So allocating interactive session in Bridges-2 is quite simple. You just need to use interact command. And we are since this for this tutorial, you don't even need to use a GPU, but it's pretty small graph. But for if you are dealing with real problems, then you may go to like GPU for simulation. Here we are allocating like one node and then 128 task per node, and the time is like 2 hours here. So the CPU backend in CUDA-Q is OpenMP, uses like OpenMP threading library. So you just need to uh, like allocate the task per node. And you can also like use interactive session with like V100 node. And we also have other GPUs available, including H100. And I just want to make sure that when you use this, you should only use this when it is needed, because it is charged at the twice the credit rate compared to other GPUs. So once we have open our interactive session, then we can open our apptainer cell using apptainer cell command. And these two flags are used to make sure that our home environment doesn't interfere with the container environment. And for GPU, we can use this dash dash NV flag. But if you are only using CPU and CPU backend, then you don't need to use this flag. And in the maxcode.py, there is a line where you can set your backend target. Like for example, for CPU, you can use QPP dash CPU target, and for one GPU, you can use NVIDIA target. Apart from that, you can also change the precision of the calculations. I think for these, the default is double precision. Uh, I think it's a single precision uh, in the CUDA-Q, but you can change it to double precision. So once you have changed that, then you can simply run Python maxcode.py to run the calculation. And if you don't want to open the cell, you can directly execute those command using apptainer execute command and give the path to container, and followed by your command to run the maxcode.py script. And in batch submission script, you can use uh, batch submission script and submit the job to cluster using sbatch command. So this is how you can perform these calculations, and uh, I will make sure you will get those repo and also recorded demo so that you can like explore on your own time. Next, let's discuss what the results we get. So here on the beginning of the slide, earlier slide, we have printed out the optimized value of those parameters. Now we are using that parameters one last time to sample our circuit over like almost like the I think the by default it runs for like 1,000 times. And you can say we can print the bit string something like this. And uh, the first number here corresponds to the first node here, like index by 0, and the last is where is that? I think it's the 9. And you can see that the first is the we have encoded the 1 state by the red color and 0 state by the blue color for so that we can clearly observe the difference. As you can see, the first is red, then followed by 3 qubits in the blue. That means we have 0, and then we have 5, 1, 2, 3, 4, and 5 in a red, 4 and 5 in a red, and then 6 in a blue, 7 and followed by. And if you compare the chords, I have highlighted these chords that has two different type of nodes in a green, If you simply count that, we have obtained like 11 chords. And if you simply draw this a line from like this, connecting all these edges, you can simply see a picture where you can partition both these red and blue states separately. So for this calculation, I have used 5 layers, but even we can convert this result less than 5 layers. So these are the results for different layers. I have used the initial parameter like minus pi over 2 to plus pi over 2. And we can see that at least 4 layers is of the quantum circuit is needed to convert the result to 11 cards. So apart from that, there are other examples in CUDA-Q. You can explore for this, like solving these problems. And so there was a video link I was talking about. You can simply uh, access this link using here video link. Just simply click it here. And so far I have discussed some of the backends like CUDA-Q has, and we have a very short course on learning management system, our PSC learning management system, where we have discussed some introductory CUDA-Q basics and then different simulation backends from CPU to TensorNet backends. You can check out those courses as well. And these are the reference. And I would like to thank you for attending the talk like very enthusiastically. Yeah. And there are other slides you can explore from like CUDA-Q basics, which I did not cover in this talk. Yeah.
Thank you, Niraj. Thank you very much. So, I don't know if you can see the questions in the Slack here, in the chat.
Let me.
So I think the first one, I think Mohammed had a couple of questions. I don't know, Mohammed, you want to ask them yourself or Niraj, you can just look at the slide. So the first question from Mohammed was, can I ask please how UHAT is founded? And then he had,
You mean the time evolution operator?
Yes.
I guess.
Yes.
Yeah, that's it's like basically like you have to solve time dependent Schrodinger equation, and that leads to different like quantum mechanical lecture. But as I have showed you the expression to compute that, right? Let me share that again.
And then he also asks, I also don't get it that you started with
So
H
here
for
you can
cos
see
H.
over here. Can you see the slide?
Yeah. Yeah, I can see the slide.
So this is the formula for time evolution operator. So we started from this integral, we discretize this integral, and then it becomes simply the product of exponentials, right? And then we have these two terms that comes from our time-dependent Hamiltonian we define for the adiabatic evolution. And and then we split these two operators using Suzuki. Let me see. Yeah. So
Mohammed,
using
you
this
had another question as
Suzuki-Schroeder
well?
expansion formula, and then we substitute, right? We have simply this multiplication uh, here. So this means we have like we can substitute like j equals 1 to all the way to p, and you have exponential for like j equals 1 dot exponential for j equals 2 and all the way up to p layers. And then you can see that over here. So I haven't shown the term in the middle, but this is how we have this. So this exponential, like product of exponential, is basically the time evolution operator you had. So
I
does that
see.
answer your question?
Yeah, thank you. Yeah, thank you.
And then there's this question from Connor. How do you determine an appropriate amount of layers?
So yeah, I mean, it's basically you have to uh, find it, right? You have to converse your calculations in terms of like different parameters. One of them is the layers. So you simply start from very small layers and then start increasing it, and you will eventually find the max code or any optimization problem you deal with in your daily work. So that's the way you have to converge it. I think it's very difficult to find in advance like what kind of layers you want to use. But ideally, you have to use like infinite layers, like p layers. But basically, for this problem, infinite number seems like four layers, right? So it's basically depending on your problem size or something like that.
Excuse me. Sorry for the interruption. But if we have too many layers on the actual quantum hardwares, well, I mean, a lot of layers will cause extra errors. Thank you.
Yeah, I mean, more layers you have, if your quantum hardware are not precise enough, uh, you will have some form of errors, right? But the error will be much much less if we simply construct a whole Hamiltonian of 2 to the power n times 2 to the power n operator and act on those state. So the error level there is much more than error level in this scenario. So I mean, you use better than nothing, right? So for NISQ era, there will be error, but when you start like self-consistency all the way, there is a chance that you will eventually lead to minimum energy somewhere.
So do you also mean that we can take several trials on the quantum simulators before we launch them or scale them in the actual quantum hardware?
I mean, definitely you can do that, but for the standard QAOA algorithm, so this is how you do it. So this is the standard setting, like this is the standard path you want to follow, right? But I have shown you like different flavors of QAOA, right? Where you can tune your can you see this slide?
Yes, I can.
Yeah, here you can see like how things can be changed to that lead to different form of QAOA and how. So this is basically this is a overall like very basic algorithm, but you can tune on your own way, right? Because there is not a single path to get from mixer Hamiltonian to cost Hamiltonian. So you can use other type of path as well. But eventually, you should get the same thing.
There was actually a question whether any of this work actually used quantum hardware.
Not here. We do not have a quantum hardware yet. So that's sad part. But this is basically CUDA-Q is basically used for quantum simulation. You can mimic the quantum hardware in your classical machine, how they works in terms of results or when you are exploring this algorithm. But yeah, you can also use quantum hardware, but there you also have to think about the errors, because the quantum hardware are prone to a lot of errors. You have to use some sort of quantum error correction or mitigation method. So that has a very separate field. But for this calculation, it's simply the simulations, right? Quantum simulations.
And specifically on GPUs, right?
Yeah, CPU, GPU. So for this one, the problem size is quite small. You can simply use CPU, but when you learn this, you can simply create your own graph using ChatGPT or something like that, and then use those. And you can see when you have like bigger graph, maybe hundreds of or more than 50 or 100 qubits, then you start to notice the slowness or difficulties using CPU. Then you can easily go to GPU on that case.
And there was also a request, Niraj, if you could, to put the link to the GitHub in the chat here before
Uh,
people leave.
so yeah, so this slide will be available to you for to explore, and then in the slide I will show you where these are. So there is a
Yeah, but
GitHub.
maybe you can put it like in the chat here. If people already want to look before we post the slides.
Okay, yeah, that can I think I can do.
Can I also ask, please, that if somebody who is not the the student at University of Pittsburgh. Like I'm from Maine State, so can we also use like PSC resources to run our like codes on Bridges-2, and like how does that works?
Yeah, I think you can apply allocation through Access program.
Yeah.
You simply fill up some form and then get access credit, and then you can spend those credit any of our machines. I think you can use those credit even more institution than ours. Like yeah, there are a bunch of, but to use PSC Bridges to you can like go through access allocation. I think if Sergio can just give you the link for the user to explore.
Yeah, you can, or I mean, you can just Google, access
Yeah,
allocation. But let me
Okay.
see if, I mean, I can try to find it now and put it here, but I'm just going to Google like you would. Access allocations portal, that should be good.
yeah. I will also leave the link of the recorded demo as well. Let me do that.
I got it. All right. Well, thank you very much, folks. Niraj, do you think it would be okay if people think of questions later that you maybe also put your email
Yeah,
address in the chat here?
yeah. Let me record the video. So email would be yeah.
Cool. All right. Thank you, folks. Thank you very much, Niraj. That was great. And just for your information, maybe you already know that and have registered, but we have another quantum computing webinar in the Bridges-2 series right this Friday. So if you haven't seen that, look for it. Thank you.
Thank you, everyone.